Howdy. So here we are. This is going to be a demonstration of my general purpose generic I/O board for my RIBBIT65 6502 based computer, which is inspired by Ben Eater's 6502 computer design and is compatible with that design. So yeah, why don't we get started? I've been toying with the idea of doing something a little differently with this stream, and I thought what I'd do is put together a slide presentation just to kind of make sure that all the talking points are hit, and just kind of expose the text of what I mean to convey, and kind of give the thing some structure. So we'll go ahead and get started with that. So if you will bear with me for just a moment, I will first slide, and poof, great. Okay, so here goes. I will do that, and I will do that, and hopefully. Interesting. Okay. Oh, I know what the problem is. There we go. All right. So, the Genio, right? It's a I/O board based on the Western Design Center WDC65C22, and it's intended to be used with machines which use the same memory map, at least as relates to I/O, use the same memory map as Ben Eater's machine. So, for starters, let's take a look at the RIBBIT65, which is my interpretation of Ben Eater's design, right? It's got a 40-pin bus connector, which I call the RIBBIT65 or R65 bus. It's got a 1 megahertz clock oscillator, an external clock source is available on the RIBBIT65 bus. So the idea there is, if you have watched Ben Eater's video series on Hello World from scratch, he's built a clock module to allow him to run the 6502 much slower, or single shot the clock on it. So I wanted to be able to have that capability because the RIBBIT65 is kind of an educational machine. So having that capability there is useful. There's some switches and lights for the CPU and control signals. And what I'm going to do is I'm going to grab my RIBBIT65 and I'm going to show it to you. So this is, there we go. This is the RIBBIT65. So there's the CPU, the RAM, a ZIF socket for the ROM, clock oscillator. This is the 40-pin header for the RIBBIT65 bus. This is address decode logic to separate the RAM from the ROM. These are just LEDs for excuse me, LEDs for CPU control signals. These are switches for like reset and interrupt and all that kind of stuff. This is an early design. This is actually the first revision of the board, the first version of the board. And so there are some things that I could have and should have done better. For example, having these lights driven through some kind of a buffer, having these switches isolated through some kind of gates or something like that. But other than that, this is the RIBBBIT65 board. So let's talk about the RIBBBIT65 memory map. So this closely follows what Ben Eater's memory map is. The first 255 bytes are what's called zero page, which is a function of the 6502. That's just baked into it. And if you're familiar with the 6502, you know what I'm talking about. The second 256 bytes are the CPU stack. And again, this is baked into the 6502. You are stuck with that stack size. From hex 0200 to hex 5FFF is user RAM, and that is the space in the 32K, so that's 24K in a 32K chip. And that's where Ben Eater's design takes over. Ben put I/O at 6000 hex, and basically that whole 8K block is out the window as far as RAM is concerned. Now, of course, that seriously simplifies the address decoding logic, but it does make things a little tough in terms of trying to make maximum use of the available RAM space. So what I did was I looked at this design and I thought, gee, it seems a terrible waste to take that 8K and just throw it out the window. So what I thought I would do is I'd at least put in some functionality so that you could have up to 16 65C22s for I/O, which would give you, a fair amount of I/O capability, and it could be stuffed into one page of that RAM space or that memory space. I haven't quite decided what I'm going to do with the rest of that 4K, but I may do something with it. I'm not sure. Maybe video RAM, something. I don't know. But then beyond that, I want to have 4K of cartridge ROM. And the notion behind this cartridge ROM is to be able to do cartridges like you could with, the old Atari computers or Commodore 64s. ROM-based cartridges are really handy for being able to just stuff a program in. So that's what I decided to do with that 4K. And then, of course, we get up to hex 7FFF. 7FFF. And that is the top of RAM, and then the rest is system ROM. At the very top of system ROM is reset and interrupt vectors. Now, the Genio uses an address most significant byte of hex 60. The high nibble of the LSB selects which 6522 chip we're going to be talking to, and then the low nibble of the LSB selects the 65C22 register. So, oops. Let's get out of here, and I can show you the schematic for the Genio. So we will go like that. So this is the Genio schematic, and this is the Rev 1 with the newer address decoding. this is the portion of the circuit that does the MSB select. So this is hard wired, right? So we've got A8 through A15, with the exception of A13 and A14, going through these OR gates, right? And the idea is if any of these address lines is high, we'll get a high, which means we should not be listening, right? So it goes through this inverter and then goes into this AND gate. Here we have A13 and A14 going into an AND gate. The idea being A13 and A14 both need to be high in order for us to work properly. Excuse me, tickle in my throat. So if we have if we have a high here, which means all of these address lines are low, and we have a high here, which means both of these address lines are high, then we have a high out, we come in here, and we AND with the system clock. Now, the purpose of this inverter and this switch here arises from the fact that the first revision of the Genio board, I wasn't sure whether I was using the clock signal correctly, whether it should have been inverted or not inverted. So I just put an inverter and a little switch in there, and rather than having to put a bunch of bodge wires and all that kind of nonsense. So that's what that's for. So we take our clock and our correct MSB value here, we AND them, and then we get the IO chip select 2. But IO chip select 2 on the 65C22 is active low. So we invert it and we get IOCS2B. Bar over the top, vinculum means active low. So that's the address decoding for the MSB of the address. The LSB of the address, the upper nibble, is handled through a combination of this dip switch and resistor array, and these XOR chips, or XOR gates, and these AND gates. So basically, when all of these switches are open, we're presenting a high to all of these things, which means the address line needs to be low in order for you to get a logic true out of this gate. So the B on these tags indicating an active low is kind of a little misleading, sort of. It all depends on your perspective. So, but the point here is, if this is putting out 5 volts, if it's a logic 1, then the address line, the corresponding address line, has to be a logic 0 in order for you to get an output here, and vice versa. If this is a logic 0, then the address line has to be a logic 1 in order to get a positive, a true out of this gate. The same applies to the other 3 bits of the nibble. You have to have all 4 nibbles reporting true through these AND gates to get your IO chip select 1. And that's pretty much how this works. Now, this little LED, the intention of that was just, if you're running at low speed, it would be useful to be able to see, without hooking anything up to the ports up here, whether or not at least the address decoding is working correctly. So these are just bypass caps. These are the power connections for the ICs. This is the 65C22 itself. This is the R65 bus, and these are the 2 ports coming off of the 65C22. You'll notice that, I'll point it out, that each of these ports also exposes a VCC and a ground. Just in the interest of convenience. So that's the Genio schematic. It's not all that exciting, I guess. So back to this slide. Oh no, I didn't want to do that. Memory map. Sorry. Okay. So we've gone through this. We've looked at the schematic. So let's talk for a moment about circuit board design. Let's go over to camera 2 here for a second. So this was the original PCB design for the Genio, and whoa, come back, Herman. Here we go. This was the original design, and it was okay. Apart from the fact that the address decoding logic was bad. So I had to fix that, and fixing that required using different chips, as well as how the chips were connected. So basically I had to respin this board. So this becomes a wonderful, I don't know, coaster, something. Here we have Rev 1.1. Now, the right chips are being used. The board layout's a little better from the standpoint of having the ports near the edge as opposed to up here. The bus connectors over here. You got the little LED, and the little switch is up here. And it worked pretty good, except for on the back. Now, the eagle-eyed among you might very well notice that this bit of ground plane, so all the filled area on the back here is supposed to be ground plane. These 14 pads are a 7400 series logic chip, right? So, yeah. So, this is the supply, and this is the ground. And if we zoom in, I don't know if we've got enough. Let me maybe throw some more light on this subject. Maybe that will help. That will not help. Come on. It doesn't want to focus. All right. So if you look carefully, you'll see this thermal relief business here, right? But this ground plane is connecting to this pad, right? As it should be. But the difficulty is that because of all the vias that I had to do on this, and because I wasn't paying close attention, basically these two vias, especially this one, and this selection of vias down here, made this piece of ground plane an island, right? It isolated it from the rest of the ground plane. So that meant that this ground pin on this IC was floating, which resulted in, oops, come back, Herman, which resulted in all the outputs on this chip, which, if I remember correctly, is a 7408, an AND, quad AND gate. All the outputs were floating high, which was bad. So I have done a redesign. I haven't sent them out for manufacturing yet, but I've done a re-layout, moved these vias up, and so there should be a good connection across here to allow this pin to be properly grounded. But fortunately, this is sufficiently not terrible, that I was able to bodge it with a little hunk of wire and a little bit of RTV, and that fixed it. So this is the finished Genio. Now you may also notice that port A and port A, well, that's wrong. That's a problem with the silk screen. That is my fault in laying out the board. So that has also been fixed on Rev 1.2, which again has not been sent out for manufacturing. And the label on this chip, the 64HC06, that's wrong. That should be 74HC86. So that's the XOR there. So the silk screen issues have been fixed in the new version of the board. So if there's interest in this board, either as a kit or just a board or just the design files, I will not be publishing Rev 1.1. If you see Rev 1.1 in the wild, that's wrong. You should be looking for Rev 1.2 or later. Also, possibly of interest to the wider 6502 community is I have done a rework of this board again to be to basically allow you to, with dip switches, set the MSB, the desired MSB for the address that this is looking for. It adds a 7th logic IC because it requires 3 XOR chips instead of the 1 to accept the dip switch inputs. But other than that, it's roughly similar in layout to this board. The dip switches are all up here. I think the new board is slightly larger. I haven't taken a measurement in KiCad, but the dip switches are up here. I think the LED is in roughly the same relative place. The 65C22 is still down here, and the ports are down here. So, but at this stage, I'm not going for any mechanical consistency between the boards or, throughout the ecosystem. This is primarily demonstration, proof of concept, that kind of thing. So that is the Genio. That's not the end of the thing. That's not the end of this presentation. That's just, this is the Genio board. So let's get back into here. So, yeah, ground plane moat leaves U5 pin 7 floating, corrected with a bodge wire. We've seen that. The silk screen label for U4 should be 74HC86. And both port connectors are labeled port A. So those faults have been fixed in Rev 1.2, which has been designed but not sent out for manufacturing. In order to ensure that the Genio works and can work in any of the 16 locations in memory, or yeah, the memory map positions, the 16 different memory map positions, I wanted to have an exerciser program that would allow me to hit each of those and send data out, at least doing writes. I mean, as far as handling interrupts and all that kind of stuff, I haven't figured that out yet. Handling interrupts across 16 different I/O devices and making sense of that, no, I haven't figured that out. But at the very least, being in a situation where I can reliably send data out to all 16 of those I/O devices. That's what I wanted to be able to do. So basically, I wrote a machine language program with 3 nested loops. It does a write only from the CPU to the Versatile Interface Adapter, the VIA, the 65C22. It's sending 1 byte to each of these, each of the ports on each of the 16 vias. And it starts at hex FF and counts down to hex 00. So basically, the innermost loop is going through all the ports on all the vias, right? So there's a test value, and then it cycles through the 16 vias. Then it decrements the test value. It goes through all the vias. Then it decrements the value. It goes through all the vias. When it gets all the way down to 0, then it just starts over. It resets the test value to 0. It resets the counter, the via counter, to 0 or to 15. And that's how that works. So, and again, it's sending stuff to both port A and port B on each of the vias. So it's hitting 32 channels, I guess you could say. So let's take a look at the exercise program. If you'll bear with me for a moment here, I will bring that up now. Oh, I thought I had that set aside, and I don't, because I'm terrible. Listing. There we are. Okay. So here we go. This is the listing. I borrowed this from Ben Eater's Hello World. It's really not of any great importance. I can probably just remove it or comment it out, but I was using his Hello World as kind of a starting point. But here's a bunch of constants that I set up, right? Basically IO start, and that's the hex 6000, that's the beginning of the IO space. But then I realized I needed to have it as an MSB and LSB in order to write it out to the write it out to memory in 0 page, because basically I'm going to be referring back to 0 page in order to get the initial values so that I can reset my working values. These are addresses in 0 page. In fact, no, these are not addresses in 0 page. These are the register numbers for the data and the data direction for the 2 ports on a particular 6522 that we're talking to. These are the 0 page addresses here, right? So this is the location, the vector IO start, and this is the vector for IO work, right? So IO start is just the initial value. IO work is the working value. So as we're going through the loops, we're incrementing the value in IO work. So let's see. So so this is the IO count value. So again, that starts at 15 and then decrements. This is the initial value. This is the working value. This is the initial test value, which starts off at 255. As we work through, the working value will decrement. So these are the addresses in 0 page where those values will be stored. This is just getting all that stuff set up. We write to VIO start, we write to VIO work, we set the initial and working IO counts, we set the initial and working test values, and then we label the tops of our 3 loops. This is just a comment in case it occurs to me later that I need to put anything to set up the loop. But as I've written it here, there's no setup required. Loop 2 just loop 2, which is the 3rd loop, the innermost loop, right? So basically we just set the DDRs, the data direction registers, to write on all 8 bits. And it occurs to me now that it might be interesting to do as as a further exerciser to make sure that, you know, the data direction register stuff is working properly, to start shifting that DDR one way or the other, so that we're writing fewer and fewer bits. So as you're running through the exerciser, you can see that the changes in the data direction register are actually being registered, for lack of a better term. But that's for a later time. This is just a minimal making sure it's working. We write the test value to port A. We write the test value to port B. We write the test value to port A. We increase the I/O working address by hex 10, so that moves us to the next 6522. We decrement the I/O count, and then if decrementing the I/O count results in a 0, that means the 0 flag is set, which allows us to do an equality test, right? Or act as though an equality test has been done. So what we do here is, if this decrement didn't result in a 0, then we're going to do loop 2 again. If we did get a 0, then we're going to fall out of that loop, and now we're back into loop 1. And loop 1 is just going to do a reset of the working count back to 15. We'll set the working I/O vector back to the initial value. We'll decrement the test value, and if test value is not 0, then we're going to repeat loop 1. We're going to branch back up to the label loop 1. If decrementing the test value did reach 0, then we're falling out of loop 1 and we're back to loop 0. So we'll do a reset of the test value, a reset of the I/O counter, reset the I/O address, and then jump back up to loop 0. There's no condition here. It's just, this runs forever. And finally, this is setting the reset and interrupt vectors. So the interrupt vector is going to hex 0000, which is the beginning of 0 page. Not the smartest, best thing to do, but whatever. There's, apart from the push button switch, there's nothing that's generating interrupts in this arrangement anyway. So at least currently. So that's fine. So this is the listing. It's with comments and white space. It's 150 lines. Not so bad. Let's see. Let's go back in here and let's see if I can do this. Oh, look at you, you son of a biscuit. Where were we? Genio Schematic. We already looked at that. We talked about the issues. We did the listing. Okay. So let's go back in here and start from current slide. So we've done that. That was a lot of fun. Oh, let's do a demo. Okay. So it's going to take me a few seconds to get this set up. if you will bear with me for just a few minutes, let me get this set up, and I'll be right back. Howdy. All right. So, we're back. So, let's do a demo of the Genio with the exerciser program loaded in. So, I have an EEPROM that I've installed in the R65 that has the exerciser program already burned. Save us a step here. And so let's switch over to the overhead camera, and let's do the needful here. So this is the R65 with the Genio installed, and this is one of my BusyBox boards. I'll discuss these a little further after the demo and stuff, but basically this allows me to have lights, latching switches, and momentary switches that I can connect to breadboard projects, or as in the case of this, just hook up to the port B, I believe that is, no, port A on the Genio. So the value of that is I don't have to futz around with breadboards and jumper wires and all that other, and resistors and all that other nonsense in order to get some lights or some switches to connect to other things. So the ROM is in place, the Genio is mounted, the BusyBox is there. All we need to do is apply power and possibly reset. No, starts right up. So you can see these lights here are clearly blinking. These lights here appear to be constantly on. That's just because of the fact that the count down of these are the high bits, right, of the test value, and it's just cycling through the test values very rapidly. Now, just to demonstrate that the various 65C22 address positions are working correctly, and unfortunately we can't really see much in the way of illumination from this LED, but if the clock was running slower, we would see that. But what I'm going to do is I'm just going to change the bit 2, and we can see that the lights are still blinking down here. I'll change bit 4, and we'll see that the lights are still blinking. So that's reassuring. And that is the that's the exerciser. So we gather from this that in fact the 65C22 address decoding is working properly, and that the 65C22 is working, right? So that's great. Now let's go over here real quick. So the next thing we want to do is demonstrate Ben Eater's Hello World functionality, and that requires that we have a 2-line LCD connected, and that we're going to be using both ports on the 65C22, which is kind of a further test of, you know, will it blend? So I'm just hooking that up right now, and hopefully everything will be in shot. Let me zoom in just a little bit. And okay. So this is the Genio. Bring that over this way a little bit. So we got the Genio hooked up, both ports. Make sure I'm doing this right. Okay. So yeah, both ports go into the breadboard, and the data bits are easy enough to hook up, but the control stuff is a little wonky. So that's what this mess of spaghetti is about. Oh, you know what? This isn't going to work until I change the EEPROM. So I gotta, if I don't want to lose my mind trying to snake this thing out, ZIF sockets are your friends. So I'm gonna pop that out and put that in foam and pop this in. Okay, so that is the Ben Eater Hello World EEPROM machine language 6502 machine language program. We'll drop the Genio back on to the bus. Apply power, and with any luck, we will get a hello world. May have to reset first, but yeah, so I'm going to go ahead and reset. And with any luck, let's see, can I shade that? Does that help? That does not help. Now, let me try zooming in a little. Well, there we are. Hello world, right? So, so that works. I can reset all day, and it almost doesn't even, I mean, it runs so fast it doesn't even give any indication that that it has to do anything. And the active LED on the Genio is also not lighting in this setting either. So move these out of the way so you can see. Yeah, it happens so fast you can't even see it. But the good news is that works. So let me just take a quick look at the stream and the chat. So it looks as though we don't have much in the way of activity on the chat, which is fine. But as far as Q&A goes, we're gonna skip that, and we're gonna go right into talking about the BusyBox stuff. So I'm just gonna disconnect the power here, and I'm gonna move this out of the way. And talk about BusyBoxes. So the idea here is pretty straightforward. These three boards, I zoom in a little bit. You know, one of the things that I've encountered in playing with, you know, these retro computer things is that it's hard. It's a complete pain in the neck to do monitoring of the buses and the various control signals and all that kind of stuff. And yes, you can use a 8-channel, 16-channel, 24, 32-channel logic analyzer, but getting everything set up and actually like lining up what the signals are and decoding it all, that's kind of a pain in the neck. And you can use a logic probe to kind of go around and see whether things are doing what you want, or you can use an oscope. But all of those methods are kind of clunky, and it's hard to get a straightforward view of what you're looking at. So what I wanted to do was to be able to say, all right, I need and to do it on a breadboard, to do like LEDs and switches and stuff on a breadboard. Yeah, you can do it, but it takes so much extra setup time to do all the wiring and place the components. And oh gee, I ran out of space on this breadboard. Let me grab another one. Oh, I'm out of breadboards. Let me buy one. You know, it's just nightmarish. So what I wanted to do was to be able to say, all right, I need switches, I need lights. That's what I need. I need some momentary switches. I need some latching switches. And so what I wanted to do was come up with a small board that would give me lights, latching switches, and momentary switches. And that's where this little baby came in, right? So this is my first busy box, and I had several of these made. I've stuffed and soldered 3 of these, I think, because I wanted to have 16 address bits and 8 data bits. So that covered that. Then, you know, after playing with this for a while, I was like, you know, I'm doing latched stuff for data and address. It might be handy to just have one busy box that has 32 switches on it. So that's where this came from. And then I thought, similarly, it would be nice to be able to have one central place that has 32 lights on it. And that's where this came from. Now, this one is a little different than these in that the inputs to all these lights are buffered. So that's what these chips are, right? So that means that the loading on the connections is minimal, which is good. This busy box has these 2 chips here. These are inverters, and basically what this allows you to do is on this connector, this is just a standard 40-pin connector. On this connector, these switches are represented as both active high and active low. And some of these switches are represented as both active high and active low. The idea being that for some things like the reset signal on a 6502, right? That's RSTB, right? It's an active low. So you want to press this button and you want to say that's reset. Well, okay. One of these connections is this button's active high, and there's another connection on there that is high until you press this, and then it goes low. You know, there's debounce caps here. These are just resistor networks to pull high or pull low as needed. Same thing here, right? So, and these are the current limiting resistors done as resistor networks. The eagle-eyed among you may notice that these are 10-segment barcode displays, but I report this as 32 lights. Well, that's because 2 lights on each of these displays are unused. It's imperfect, but the components are cheap enough that it justifies, as opposed to trying to track down 8 light devices. So the next thing I want to do in terms of busy boxes is make a single unified busy box that would allow me to connect to the R65 bus and just say, set addresses, set data, set or control the CPU control signals, and huzzah, you know, that would allow me to, in theory, manually test a board. I might even integrate some kind of like low speed and single shot clock functionality on such a board. I'm not sure at this stage. We'll see. But anyway, I'm thinking seriously about doing a like an 8-bit CPU dev / test specific busy box. But that's not what's going on today. So these designs here, these busy box boards, if anybody's interested in these, shoot me a comment on this, and I can get you the design files. I don't have a GitHub yet, but I will probably be posting when/if I set up a GitHub repository. I'll probably be posting the design files for these boards. But yeah, so those are the busy box boards. And I think that pretty much covers everything that I was planning to do for this stream. So so that's the Genio. When I do spin up the Genio 2, I'll probably be doing a stream on that. I don't think I'm going to do a stream for the Rev 1.2 on the original Genio, just because it's fixes. But the Genio 2, I think, warrants a quick demo to show the different functionality, and certainly for other types of 6502 projects, and I guess even like Z80 projects or 8080 or whatever, as long as you're planning to use the 65C22, the fact that the thing can address to anywhere in the memory map, as long as you're starting on an address where the 4 low bits are 0, that's probably advantageous. But in any event, that's I'll probably do a quick stream on that once that's done. But for now, I think that's it. So thanks for watching. If you like my content, like and subscribe. And if you think anybody else might be interested, please tell your friends, share. Ribbit Nerding is on Facebook. Ribbit Nerding, just search for that. And I think that's about it for now. So there's links in the description for KiCad, which is a software that I used for designing these boards. Ben Eater's website, eater.net, a really good resource. He's a great guy. Check out his YouTube stuff. I believe there is a link to the Ribbit Nerding page on Facebook. There's also a link to Jameco, which is the company that I bought most of the parts for these projects. The 65XX chips, the 74XX chips, IC sockets, all that kind of stuff. That almost all of that stuff comes from Jameco. Check them out and give them some business if you like what you see there. And let's see, what else? There's something else. Oh, JLC PCB. There's no paid promotion or anything like that. Just this is the board house that I've been using, JLC PCB. There's a link to them in the description as well. So thank you for watching. Let's do this again sometime, huh? And I guess I'll do a stream a little later, kind of going through the vision for further RIBBIT65 development. But I think that's going to do it for now. So thanks for watching. Like, comment, subscribe, share if you like, and we'll talk to you later. Thanks. Bye.